Hey, so I'm Everett, and this is my lab report for Lab 3 in Physics 2212. Um, so to start off, the purpose of this lab is to compare the effect of changing distances or distance dependence on the magnetic field from a magnetic dipole, specifically a bar magnet, and this is measured both on and off axis. So for the models, we're going to be using the model of a magnetic dipole according to the Biot-Savart law, which has an equation I'll get to on the next slide. And then a sneak peek at my results. I got that n, which is the exponent of the distance in the magnetic field equation, is approximately -3. The magnetic dipole moment of my magnet was around 2.44. The magnetic field at the off-axis location was 36 microteslas, which is what I measured, or 27 microteslas, which is what I calculated it should be. So this lab deals with magnetic dipoles, which can arise from a couple of different situations that, while they look kind of different up close, have similar or equivalent behaviors at a distance. Specifically, we're going to be looking at a dipole with two poles, although that doesn't really matter since we're not going in between the poles, so it's going to look the same at a distance. And these dipoles are pretty similar to electric dipoles, with their magnetic fields looking similar and the electric field to the electric fields, and the relationships being kind of similar. And then we're going to use a couple of pre-derived formulas. The big one is the general formula for the magnetic field from a dipole, which is the bottom one here, but we're also going to be using the on-axis formula to find the dipole moment of the magnet later. So there are a couple of parts to this experiment. The main part, so our system consists of the phone and the magnet, but it also technically includes the Earth because that does mess with measurements. So first thing we do is we line up the phone's magnetometer with magnetic north, so that the x component of the magnetic field will only be coming from the magnet. And then we measure the distance from the magnet required to achieve different magnetic field values, like 20 microteslas, 70 microteslas, 120, etc. And then we record those in the table, which we'll use later. And then we also find a distance where the magnetic field is 100 microteslas and move that same distance perpendicular to the axis of the magnet and measure and record the magnetic field at that point, which we will also use later. So to get to the results, you did need to do some work for this experiment. So if we assume that the magnetic field has some linear relation to a power of the distance from the magnet, so B equals K R to the N, we can compare the logs of the distances to the logs of the fields and take the slope of the best fit line to get the exponent. So here I got that the slope should be -2.75 or around 3. And then to get the magnetic dipole, we're going to do some work with the intercept of that equation, because the K in this B equals K R to the N should be the intercept. So we also know from earlier that this K is going to be equal to mu naught over 4 pi times 2 times the dipole moment. So if we take this K that we figured out from the intercept and divide it by mu naught over 4 pi times 2, we can get that the dipole moment is around 2.44. And then we also have here is the average net magnetic field at the off-axis location, which is around 36 microteslas. So for the coding, I implemented the general equation from earlier as shown here. That was just some Python. And then I plugged it in a couple of distances to show the magnetic fields around the bar magnet and also to compare with my measured values. So I used the measured distances and I got magnetic fields that were within around 15-ish% of what I measured in real life. So I thought that was pretty accurate. Then I plugged in the distance from the second half of the experiment with the off-axis location, and that was around 17 centimeters, and I got a value of 27 microteslas, which is a bit less than the measured value, but still within a reasonable range. And then finally, for some analysis, my assumptions, I assumed that the Z component of the magnetic field was negligible, since there shouldn't be any Z component from the magnet. I assumed that the phone was properly oriented north, and the magnetometer had been correctly located within the phone, so I could get measurements correct. Some error sources are the magnet and the phone not being properly oriented. I placed them in grass, so they could have moved when I put them down. And then another possible source is nearby electronics, my computer, which was kind of far away. It was still within arm's reach, so it might have been close enough to interfere. And the questions, if I hadn't oriented my experiment to compensate for magnetic north, then the b equals kr to the n equation would have a constant term added to it, which would totally mess up the work we did with logarithms. And then if there were two magnets added end to end, if we assume they each had an equivalent dipole moment to my magnet and they were relatively small, the field at each location I measured in the experiment would double because each magnet would act on it, so it would act on it twice.